Hello, in this video we are going to see how you can simulate a coplanar waveguide without ground in CST. So in case of a coplanar waveguide, we know that the signal trace and the ground are on the same plane. So this is the dimension of the structure that we are going to simulate, where width of the signal trace is 1.6 mm and the gap between the signal trace and the ground plane is 0.7 mm and the dielectric constant of the material is 4.3. So this is the impedance calculator available in CST, and based on that the characteristic impedance can be uh, given as 71.13 ohm. So let's see how you can do the simulation in CST. So if you go to CST help, you can get all the details about the port dimensions and what are the important things that you have to be considered while designing these ports. So to design that, I have taken the new template and then I have gone for the antennas, then planar, time domain, maybe frequency I will be giving from 1 to 5, then next, finish. So once the project is opened, you can go to calculate analytical line impedance. So this window will be popping out and you can go for the Coplanar waveguide, and you can select the width of the signal trace as 1.6 and gap as 0.7 mm, and this is the line width, that is the length of the total structure. So I'm going to give it as 50, and epsilon r I'm going to use 4.3 mm. So if you calculate, you will be getting the characteristic impedance, and if you click for build 3D, it will ask for the physical length of the structure. So whatever I have given here, it will be appearing here. You can also change it, and you can see that the structure is created, but one of the thing you can see here that substrate width is very high, so maybe you can reduce that to 0.8. Okay, so 0.8. Oh, sorry, substrate, not substrate width, substrate height. So I have to actually reduce the substrate height, sorry. Okay, so now it is reduced. So my next step is to assign the port. So to assign the port, you can select these 2 points. So if you click on P, it will be popping out, and you can select these endpoints by double clicking and go to the port, new waveguide port. So it will show like this, and here you can provide the dimension. So based on the CST help, the total width has to be around 3 times W. W is the total width from P1 to P2, that is around 3 mm, because this is 1.6 mm. The gap is 0.7, 1.6 plus 0.7, 2.3 plus again 0.7, it is 3. So I'm going to give it as 3 here, 3 here, and the total width is they have taken as total width of the patch, so it has to be around around 3, but sometimes we may have to optimize the port dimension to get the correct result. So here you can see that this arrow direction is outward, so you can put negative here, so it will be directed inwards. So y minimum is you have to account for this thickness 0.8, then uh, you may have to give w by 2, that is 1.5, and on top also you can give 1.5. And here we don't have to use the multi-pin port, but in case of the CPW with ground plane, you have to use the multi-pin port. So in later I will show you do this has any impact or not. So now our port assignment is complete. So first our step is to make sure that this port dimension is giving us accurate results. So you can click this thing, calculate port only, and in homogeneous port accuracy enhancement will give you all the result from the defined frequency ranges. If you did not click this, the calculations will be happening only for the center frequency. So it is better if you want to have the value for the entire frequency range. And if you start, the simulation will be starting. So let's do that. So the simulation is complete. So based on the calculation, we have to get an impedance of 71.13. So let's see if we have obtained that. So for that, let's go for the CST. Okay, so I'm going to check whether I have obtained that line impedance as 71.13. But here you can see that it's very less. That means that you have to increase the port dimension. So maybe you can increase this port dimension like 2.5, and then again we can start the simulation. So first step is the port dimension checking. So you have to make sure that whatever is the impedance that you should get that from your simulation. Okay, the simulation is complete. So let's check the line impedance. So here you can see that here it is in the range of 71.3. So now you can assume that the port dimension is okay. So now our next step is to see if that electric field and magnetic field alignments are as per our expectation. So our expectation is like the electric field has to start from the signal trace and end in the ground plane. So here you can see that the electric fields are starting from the signal trace, that is the middle one, and it is ending on the ground plane. Here also that is happening. That means that the port dimension is okay, and when you consider the magnetic field, you can see that it is forming a circular orientation. That means that the magnetic field orientation is also okay. That means that this port dimension is okay. So our next step is to do the port assignment on the next uh, other direction. So let's select that one and go for the port and new waveguide port. So you have to give the width 3, and here we know that the port dimension is around 2.5 that we have optimized. So okay, so we now see that the arrow is into this structure, so it is okay. So I'm not enabling the multipin port, and now our purpose is we have to see the S parameter also. So you can untick this, so it will be calculating the S parameter, so you can start the simulation. Okay, the simulation is complete. We can check the S parameter. So if you click it here, you can see that S11 is very less than minus 10 dB, which means that whatever is given as the input here is getting transmitted to port 2. S21 is nearly 0. That means that there is no reflection back. So everything is getting transmitted. So this parameter gives a good indication that the port assignment and this waveguide whatever we have designed is pretty okay. So this port mode we already seen that. Maybe I will show you what will happen if we define the pins. So this does not have much impact. So before going to that, maybe I will save this line impedance, because this is whatever we are interested in. So I will save this. I have copied that, and I'm going to get a new tree folder, and I'm going to compare the impedance of line. So maybe I will copy that here. So this is port 1 without multipin. Okay, then I will assign the multipin port here, define pins. Okay, so for that I have to assign the pin. So maybe we can hide the substrate. So if you just click Control 8 or right click and hide, it will be hiding. So you will be having only the metallic structures, and add positive. So the positive is our signal trace, and this is it, and negative are the ground plane. So pick it and then add one more negative. Okay, select it, then close, then okay. So what I'm going to do is I am going to calculate only port modes because I'm only interested in to know whether this multipin port has any impact on the impedance calculation. Do we need to go for the multipin port in CPW? So let's start the simulation. Okay, the simulation is complete. So let's go for the line impedance, and I'm going to copy that and I'm going to paste it here. So this is the impedance with um, multi-pin port. So here you can compare the impedance. So port 1 and port 2, you can see that with and without multi-pin port the impedance is the same. So here in case of CPW without ground plane there is no need to assign the multi-pin port, but if you assign the multi-pin port also it is okay because you will be getting the expected port modes. So maybe we can check the electric field. So if you check the electric field, you can see that the electric field is from the signal trace to the ground, and the magnetic field is forming a circular thing. That means that the port orientation with multi-pin port is okay. So you can either assign the multi-pin port, or if without it also you will be getting the exact result. One of the things you have to make sure is the port dimension. You have to make sure that the port dimension is okay so that it will be giving you the exact impedance value as that you have designed. I hope you get some idea about how you can do the simulation of the CPW without ground in CST. Thank you.